Hello everyone, this is Dilip Chakravarti, Assistant Professor in Cybersecurity Department, IARE College. Today we are going to discuss you about graph. So graph is a non-linear data structure. So we all know data structure is a way of organizing the data and a set of operations that are going to perform on that data. Okay. So here graph is a non-linear data structure where we are arranging the data not in a sequential fashion. We are arranging them in a scattered fashion, or we say it as a hierarchical fashion. Okay, so there is a definition given for graphs. Uh, graph is defined as an ordered pair of set of vertices and a set of edges. So whenever you are talking about a graph which is represented as G equal to V comma E, where V is the set of vertices and E is the set of edges. So for example, for this graph, if you observe there are five vertices A, B, C, D, E, and we are having some edges A, B, A, C, C, D, B, D, and D. Okay, these are all the edges. So in a graph, we'll found these two things, V and E. Okay. Uh, so there are different terms we are going to find in graph, okay, such as vertex. So in the above graph, as I said, A, B, C, D is a vertex. Okay. So here, vertex is an individual data element of the graph is called as a vertex. Vertex is also known as node. Sometimes we'll call a vertex as node. Then an edge is a connecting link between two vertices. So if there are two vertices, if we join those two things, we call it as an edge. Edge is also known as an arc. Sometimes we'll call it as arc also. Okay. So an edge is represented as starting vertex and ending vertex. For this graph, if you observe, AB is an edge. A is starting vertex and B is ending vertex. Okay, so A, B, C, D, E all are vertices. Okay, so then origin. If a edge is directed, its first endpoint is called the origin of it. From where we are drawing an edge, that point we call it as origin. And from where we are drawing to, we call it as destination. We are starting from one point, we are ending at one point. The end point we will call it as destination, and the starting point we call it as origin. Okay. If edge is directed, its first endpoint is said to be origin of it, and the other endpoint is said to be destination of that edge. So still a path can be defined as a sequence of nodes that are following in order to reach some terminal node. Okay, so we are starting at one vertex. We call it as initial vertex. From that vertex, suppose if you want, if we need to move to some other vertex, so the way we are proceeding, we call it as a path. Okay, so for example, for this graph, suppose if you are at A, if we need to go to E, I can go like this: A to B, B to D, D to E. This is one path. A to C, C to D, D to E. This is one path. Okay, there are different paths for some vertices. Okay, so that is what we call it as path. Then closed path. A path will be closed as we are saying it as closed path if the initial node is same as terminal node. If initial node and terminal node both are same, we'll call it as closed path. Okay. Observe this graph. So if you observe here, if I start from A to B, B to D, D to C, C to A. So again, if you are reaching to the same location, we will call it as a closed graph. Okay. So that thing we call it as a closed graph. So then adjacent nodes. If two nodes U and V are connected by an edge, then the nodes U and V are called neighbor or adjacent. Okay, suppose if you consider AB as an edge, so A and B we can say them as adjacent nodes, or we can say them as neighbors. Okay, so then degree of the node. So a degree of the node is the number of edges that are connected with the node. Okay, maybe some edges are coming towards it, maybe some edges going outward from that. All the edges which are connected to that node. For example, in this one, For D, so there are three edges connected. Okay, so we will say the degree of D is 3. So degree of D is 2. Degree of A is 2. Okay, so degree of E is 1. So in this way, we are going to find the degree of any node. Okay, so a node with degree 0 is called isolated node. Suppose if there is only one node, if there are no edges, we'll call it as isolated. Okay, then in the total number of incoming edges connected to a vertex. So if whatever the incoming edges connected to a vertex, we call it as in degree, and whatever the edges which are going from that node, which are going outside from that node, we call it as out degree. Okay. So then parallel edges. There are two undirected edges with same end vertices. Okay. So vertices are same, but and two directed edges with same origin and destination. Okay. If same origin and same destination is given, so those two edges, we call it as parallel edges. To draw two edges from same vertex and same origin and same destination, we'll call it as parallel edges. Okay. Then self loop. Self loop means it's a circuit towards itself. Okay. A loop to itself, we call it as self loop. Edge is a self loop if its two ends point coincides with each other. If both are same, we'll say it as self loop. Where we are going to apply this graph theory. We are going to apply this graph theory at various places such as electrical engineering, computer networks, and other applications. In electrical engineering, you'll be drawing a lot of circuits. So you'll be drawing a lot of topologies in computer networks, how different computers are connected. See, all these things can be simulated by using this graph. First, we will be drawing a graph. Based on that, we will implement the exact design. Okay. So, and in other applications, routes between the cities are represented using graphs. I can represent routes. So, hierarchical order information such as family tree are represented using these graphs. Okay. So there are different types of graphs. So such as null graph, trivial graph, non-directed, directed graph, connected graph. So we are having a lot of these graphs. We'll see all these one by one. Okay. So we'll discuss all these things one by one. A graph whose edge set is empty is called null graph. So first we'll discuss about null graph. So if you observe, he's saying that a graph whose edge set is empty. So here, if you observe, there are three vertices A, B, C, but there are no edges between these vertices. Okay, so we'll say this one as null graph. In other words, a null graph does not contain any edges in it. Okay? Here, this graph consists only of the vertices, and there are no edges in it. Okay, I hope it is clear. Null graph means which doesn't have any edges. Okay. So then trivial graph. So when I'm going to call it as trivial graph means a graph has only one vertex. So if you observe the graph, it consists of only one vertex. Okay. So we'll call it as trivial graph. So it is the smallest possible graph. So we'll be drawing only one vertex or one node. Okay. So there are no more vertices in the graph. Then we'll say that graph as trivial graph. This graph consists of only one vertex and there are no edges in it. Okay. Since only one vertex is present, therefore it is a trivial graph. Okay. So then non-directed graph, a graph in which all the edges are undirected. If all the edges are undirected, we'll say it as non-directed graph. If you observe, there are no arrow marks there, whether we are moving from A to B or B to A. So such graphs, we call it as undirected graph. In other words, edges of an undirected graph do not contain any direction. It does not contain any direction. If you see this diagram, there are no more any connection. I mean, any direction, whether it is moving from this direction to this direction or this direction to this direction. We will call it as non-directed graph. Okay. This graph consists of four vertices and four undirected edges. So we are having four vertices and four undirected edges. Okay. Since all the edges are undirected, therefore it is a undirected graph. As it consists of all undirected edges, we call it as non-directed graph. Okay, so observe this directed graph, which is opposite to undirected graph. In undirected graph, we observe that there are no direction. So, but here their direction is given. So we are starting from A and we are moving to B, A to B, but there is no direction from B to A. So whereas in non-directed graph, A to B means, so there is a direction from A to B as well as from B to A. Okay, so here we are mentioning directly which way. A graph in which all the edges are directed is called as directed graph. Okay, in other words, all the edges of directed graph contain some direction. You are having some direction. Directed graphs are also called as digraphs. Sometimes we can call it as digraphs. Observe this diagram. So here we are having directed edges. So it is moving from A to B. Here it is moving from C to B, D to C, and D to A. Okay. So this graph consists of 4 vertices and 4 directed edges. Since all the edges are directed, therefore it is a directed graph. Then weighted graph. A weighted graph is one where each has a cost for traveling between the nodes. Suppose if we observe this graph, so from A to B, so a cost is given. Okay, so from A, if you need to move from A to B, so I need to spend this much amount of time or this much amount of money. So we are we are designating it. We call it as a weighted. Okay, so a weighted graph is one where each edge has a cost for traveling between the nodes. From A to B, the cost of traveling is 6, and from B to C, the cost of traveling is 5. C to A, it is 7. Okay, so here I have given this for non-directed graph. We have not used any directions here. Okay, so this is about weighted graph. Next, connected graph. So if you observe, if two graphs are connected, when we are going to say if two graphs are connected, okay, a graph in which we can visit from any one vertex to any other vertex. So I can visit from any one vertex to any other vertex in the graph. Okay, suppose from A I can move to any vertex. So in the graph, so then we will say it a connected graph. In connected graph, at least one path exists between every pair of vertices. Okay, so if you observe, so there is a path between every pair of edges. So at least one path will be there. So suppose I need to move from A to F, so A to D, D to F, so or A to B, B to C, C to D, D to F. So there is at least one path exists. Okay, so we can move from that location to that node to another node. Okay, so that at that time we'll call that graph as connected graph. In this graph, we can visit from any one vertex to any other vertex. Okay, there exists at least one path between every pair of vertices. There exists at least one path. Okay, therefore it is a connected graph. Next, disconnected graph. Okay, so it's the opposite to connected graph. If you observe there, every vertex is connected with other vertex. Okay, so there is a connection from each and every vertex here. But here in a graph in which there does not exist any path between at least one pair of vertex. So if you observe, I am considering only at least one pair. Okay, so you may consider here. So from D to F, I don't have any path. Okay, if there is no path, we will say these two graphs are disconnected. Okay, this is one connected and this is one connected. We can say like that. But so when you talk about total graph, this is a disconnected graph. There is no path between these pairs. Okay, so this graph consists of two independent components which are disconnected. It is not possible to visit from vertices of one component to the vertices of other component. Okay, therefore it is a disconnected graph. Next, regular graph, a graph in which degree of all vertices is same. If you observe the degree of all vertices, it is same. So for example, what is the degree of A? How many edges are connected? 1, 2. Okay. Similarly for B, 1, 2. Similarly for D, 1, 2. Okay. If the degree of all vertices is same, it is called a regular graph. Okay, if all the vertices in a graph are of degree k, then it is called as k regular graph. Here we say it as two regular graph. Okay, so as two edges are connected for all the vertices, we say it as two regular graph. So for this graph also observe here. So for this F, two edges are connected. For G, two edges are connected. For H, two edges are connected. For E, two edges are connected. Okay, so all the vertices have degree 2, so therefore we call it as two regular graph. Okay. Then complete graph, graph in which exactly one edge is present between every pair of vertices. So in every pair of vertices, one edge is connected. So a complete graph of n vertices contains exactly n C2 edges. Okay, so a graph means exactly one edge is present between every pair of vertices. So if you consider any pair of vertices, there is exactly one edge will be there. So we should not have many number of edges. Okay, so a complete graph of n vertices is represented as kn. So for example, so I am saying it as k3. So observe here for any pair of vertices. So if you take any pair, so there is only one edge, exactly one edge. There are no parallel edges here. Okay, so that's why we call it as complete graph. As it consists of three vertices, we say it as K3. As it consists of four vertices, we say it as K4. Okay, here vertex is connected with all remaining vertices through exactly one edge. Therefore, they are complete graph. Then cycle graph, a simple graph of n vertices. So when you are saying a graph as cycle graph, if we consider a graph, so with n vertices and n edges forming a cycle of length n. So observe here, so A, B, C. So there are three vertices and three edges. Okay, three vertices and three edges. So which forms a cycle, which forms it's just like a loop, we can say. So which forms a cycle. In a cycle graph, all the vertices are of degree 2. All the vertices will be having degree 2. So for this graph, if you observe degree 2, degree is 2. For this graph, degree is 2. For this graph, degree is 2. So if you observe in each graph, the number of vertices and number of edges are same. Here three edges and three vertices. Four vertices and four edges. 1, 2, 3, 4, 5. 5 vertices and 5 edges. Okay, each vertex is having degree 2. Therefore, they are cycle graphs. Next, acyclic graph. A graph not containing any cycle. If there is no cycle in it, okay, if it is not closed, we say it as acyclic graph. So here there is no edge between B to C. If there is an edge between B to C, we call it as a cycle, but there is no edge between B to C. Similarly, there is no edge between D to G also. Okay, so we call it as acyclic. This graph do not contain any cycle in it. Therefore, it is an acyclic graph. Next, bipartite graph, bipartite graph, we can say it as. A bipartite graph is graph where vertices can be divided into two sets. You can divide the vertices into two sets, x set and y set. If you observe here, A, B, C, D, I can consider it as one set. P, Q, R, I can consider it as another set. So why you are considering it as another set means? So here we don't have edges between these two, any one of among these two vertices. We don't have edges among these vertices. So similarly, we don't have edges among these vertices. Okay, we only have edges to other set. We only have edges to other set. The vertices of set X only join with vertices of set of Y. None of the vertices belonging to the same set join each other. We don't have any edges between these vertices. Okay, we call this one as bipartite. Okay, so then planar graph. A planar graph is a graph that we can draw in a plane such that no edges of it cross each other. Okay, so we don't have any two edges crossing each other. So if you observe here, A, B, we have edges. A planar graph is a graph that we can draw in a plane. We can draw it in a plane such that no two edges of it cross each other. We don't have any crosses here. We can simply draw the edges. Okay, this graph can be drawn in a plane without crossing any edge. Okay, we don't have any crosses here. That's why we are calling it as planar graph. Okay, then pseudo graph, a graph having no parallel edges. If the graph is not having no parallel edges, but having self loops, if it is having self loops in it, is called pseudo graph. Okay, so if you observe here A, B, E, the graph given, so we don't have any parallel edges here. We don't have any parallel edges, but we have still we have self loops. So it may consist of self loops, but having self loops in it is called pseudo graph. This graph consists of three vertices and four edges, of which one edge is a self loop. There are no parallel edges, but a self loop is present. Therefore, it is a pseudo graph. Okay. So then, simple graph. A graph having no self loops. If a graph is not having any self loops and no parallel edges in it, it is called as simple graph. Okay. If you observe here, it doesn't have any self loops. It doesn't have any parallel edges. If it doesn't have any parallel edges and if it doesn't have any loops, we will call it as a simple graph or normal graph. Okay, this graph consists of three vertices and three edges. There are either neither self loop nor parallel edges. Therefore, it is a simple graph. Okay. So then multi-graph, a graph having no self loops, a graph having no self loop but having parallel edges in it. So if it is having parallel edges in it, it is called multi-graph. Okay. If you observe here, there is a parallel edge between A to E. So there is a parallel edge between A to E. This is one edge and this is another edge. If such type of edges are given, such type of parallel edges are given without self loops, we will say it as multi-graph. Okay. So here the graph consists of three vertices and four edges, out of which one edge is parallel edge. There are no self loops, but a parallel edge is present. Therefore, it is a multi-graph. Okay. Then Euler graph. Euler graph is connected graph in which all the vertices are even degree. If you observe all the vertices, it is having even degree. Okay, for A, the degree is 2. The number of edges connected are 2. For B, the number of edges are 2. For C, the number of edges are 4. For E, it is 2. For D, it is 2. That means the degree of any node, if you observe, it is even number. Okay, it may be 2, 4, 6, 8, something. So we call it as Euler graph. This graph is a connected graph. The degree of all the vertices is even. Therefore, it is a Euler graph. Okay. Then we are having some graph called Hamiltonian graph. Okay. So why we are calling it as Hamiltonian graph? If there exists a closed walk, if there exists a closed walk in the connected graph, there visits that visits every vertex of graph exactly once. If you are visiting every vertex of the graph exactly once, except starting vertex, without repeating the edges. We are not going to repeating the edges. Then such graph is called as Hamiltonian graph. Okay. If you observe here from A, I can move to B, A, B, C, for any edge. If you consider any edge, if there exists a closed walk in the connected graph that visits every vertex. From A, I can move to any vertex. From B, I can move to any vertex. From C, I can move to any vertex. But exactly one that visits exactly every vertex exactly one. Okay, so we'll call it as Hamiltonian graph. So observe here, this graph contains a closed walk from A, B, C, D, E, F, G. I'm visiting all the nodes. Okay, except starting vertex exactly. Again, I am coming back to A. So all the vertices are visited without repeating the edges. Therefore, we call it as Hamiltonian graph. Okay, I hope it is clear. Uh, then uh, this is about types of graph. Okay. In the next class, we discuss about the various types of various things in the graph. Thank you.